Good afternoon, everyone. We can start now, yes. Yeah. And welcome to the Cryosphere Pavilion at COP30, which is hosted this year at the Iceland and Chile Pavilion. My name is Victoria Hochlova, and I'm representing here the Association of Polar Early Career Scientists, or APEX. I come from urban planning background, the field which is at first glance could be far away from glaciers and the permafrost. But as you will hear today, what happens at the polar and mountains regions doesn't stay there. Today, we meet the 4 early career scientists who represent the next generation of polar research. Their work helps to understand deep changes at the cryosphere and how these changes shape human systems, policy, and intergenerational justice for the decades to come. Let me introduce you our first early career scientist. It is Joseph Bonsoms, who investigates glaciers, ice sheets, and permafrost dynamics, linking them to global sea level rise and local environmental impacts.
Thank you very much. Thank you very much, Victoria, for this nice presentation. In my presentation, I will show you the impacts of climate change in snow and the implications that it has for nature and for people. Josep Bonsom, a researcher and teaching fellow from the University of Barcelona. So first of all, I will explain what is the cryosphere and what is the role of snow in the climate system. Then I will continue explaining the snow and glacier meltwater trends in the recent decades. I will finish the presentation explaining why we need to preserve snow for the ecosystem and for the human communities. So snow is highly sensitive to climate change, but it plays a key role in regulating the energy climate system because it has a very high albedo, which means that many of the energy that is coming from the sun is reflected towards the atmosphere. If we don't have these snow cover conditions, or if we don't have glaciers or sea ice, it means that most of the energy will be absorbed in the surface and will increase the temperature. Snow and glacier meltwater in the Arctic can also affect the ocean and the climate circulation because the fresh water from melting glaciers and sea ice reduces the ocean salinity, and it weakens the thermohaline circulation, and in the end it alters the global heat distribution. So here in this graph you can see the energy balance that I was talking about, where the energy is coming from the sun and then it's reflected back to the atmosphere into many fluxes that are a little bit complex, but that they are happening in the surface. Climate change is reshaping the snow season by many ways. One of the most important ways is because it reduces the snow accumulation during the winter months of the season, but it also can cause an earlier melting and shorter the snow season. And climate change can also alter the snow quality because it can change the snowpack structure. And as you can see here in this graph, the impact of 1 or 2 degrees of warming into the seasonal snow depth is quite high. But also there are other factors such as precipitation that play a key role in the snowpack seasonal evolution. So snow cover is declining overall in the northern hemisphere, and you can see this information in this map where there are represented the snow cover trends in the last decades in the northern hemisphere, and as you can see, the snow cover days are declining, and at the same time the projections of snow cover that you can see in the second graph are projected to decline quite a lot depending on the scenario that we follow. So here in this graph, what you can see is the increase of meltwater runoff in the Arctic, and we have recently evaluated the increase of runoff in the Arctic, and we have detected that there's an increase of extreme runoff probability in the western part of the Arctic, including northern Greenland, Ellesmere, Devon, and this increase of meltwater runoff is higher than the eastern parts of the Arctic. One important implication of climate change is that we have now runoff and melting conditions in other lands of the Arctic and in the northern hemisphere that in the past we didn't have melting conditions. So here in this graph, what you can see is the evolution of extreme runoff probability for different elevation bands and different sectors of the Greenland ice sheet. And as you can see, if we look at the historical period, the extreme runoff probability was lower and at the low elevation areas of the Greenland ice sheet, but because of climate change, the isothermal conditions are now happening in the accumulation areas of the Greenland ice sheet. You can see that represented in one satellite image of Western Greenland in Ilulissat. So from a climatic point of view, this is explained by two factors. The first factor is related with the dynamics of the air masses. The high pressure and low pressure systems are changing in all the parts of the planet, and part of this variability is explained because of the decrease of snow cover in zones such as the northern hemisphere or in the plateau of Asia. And then we have another factor that we call thermodynamic, and this thermodynamic factor is explained by the reduction of albedo that increases temperature, and by the increase of moisture and clouds that can increase the long wave radiation. So in the end, when we talk about thermodynamic factors, we are referring to positive loops that are happening because of climate change that increase the temperature. You have to imagine that the Arctic temperature has increased around 4 times faster than the global average, and this is related with these factors that you can see here. So without the snow, and the polar and the mountain ecosystems are totally changed. You can see that information in this graph with a representation of a snow of a mountain area with a snow cover, and then in the second plot, what you can see is a mountain area without a snow cover. And snow is very important for the ecosystem because it regulates the vegetation onset, but it has many implications that we cannot see at a smaller scale, such as soil respiration, microbial activity, carbon cycling, or other factors that more or less we can observe, such as evapotranspiration and shifts in the biological species. Snow is also very important in the Arctic for permafrost. You have to know that permafrost is the ground that remains at or below 0 degrees for at least 2 consecutive years. And normally snow acts as a protective layer for the permafrost. And around 20% of the Arctic is the northern hemisphere is covered by permafrost. So if we don't have snow, it means that the permafrost will thaw faster, and the permafrost thawing season will be larger. Mountains and snow is very important for hydrological resources. You have to imagine that mountains are the world's water towers because they provide large water for many communities that rely on these mountain and snow areas. You can see here an example of California. And the snow melted water is also a relevant resource of hydropower and resources for agriculture and water supply for these communities. Snow is also an important factor for hazards that are occurring in the mountain areas. Here you can see several examples, including snow avalanching. So climate change is altering the patterns of snow avalanching, but it has many other related hazards, such as the action of permafrost that can damage the infrastructure, or many of the transport facilities that we have over these areas. It has very important socioeconomic implications, snow. There's a large touristic industry that relies on the snow cover conditions, especially in the European mountains, where many mountain areas depend on the snow accumulation patterns, because there are many ski resorts that need that snow cover if they want to be reliable in terms of economic success. And another important implications of snow, one of the cryosphere, is for the Arctic and Alpine communities that they have an important culture and traditions and knowledge that is very related with the cryosphere. So with climate change, we are changing the landscape of these communities that depend on the snow. And I'm finishing. I just want to highlight that the snow cover projections have a very high uncertainty, but the race to preserve snow is not lost, and the future evolution of snow depends on the climate negotiations that are currently happening here at COP30. And as you can see in this graph, that shows the snow cover evolution of the northern hemisphere by the end of the century. If we decide to follow a low emission scenario, the decrease of snow cover is around 20%, but if we follow a high business as usual emission scenario, the decrease of snow cover will be of around 60%. So there's a huge difference between applying climate policies or not applying these climate policies. Thank you very much for your attention.
Thank you, Josep. Thank you very much. Yeah, your research really spans across all the different components of the cryosphere, from glaciers to the snow and the permafrost. Let's now move to the next presenter. It's Tiago Monteiro, who is a Brazilian marine biogeochemist whose work in the Southern Ocean explores how cryosphere change affects the marine carbon cycle and ocean climate feedbacks, while also leading outreach efforts to connect polar science with society.
So, hello everyone. Can anybody hear me? Okay. Okay, so thank you very much, Victoria, for your kind introduction. As Victoria said, I'm an assistant professor at the Federal University of Bahia here in Brazil. And I'm an oceanographer by background, and I study the carbon cycle and the nutrient cycle in different parts of the global ocean and in the Southern Ocean as well. So I'm talking about why I'm interested, and we are interested actually in studying the carbon cycle in the ocean environment. That is essentially because the global ocean absorbs about 1/4 of the whole excess of the carbon dioxide into the atmosphere that we release, the human activity release into the atmosphere. And most of the processes that explain if the ocean will be absorbed or release carbon dioxide to the atmosphere or from the atmosphere is explained by the processes that occur in the ocean. Oh, sorry. And most of the carbon dioxide that is taken up by the ocean is in the polar oceans, actually, in the Arctic and in the Southern Ocean. So the Southern Ocean in these regions here, highlighted by this red circle, and is the ocean that surrounds the Antarctic continent. And it's very important because the Southern Ocean connects all of the waters from the ocean, from the whole global ocean. So it's a unique place in the Earth because they connect all the global ocean in one region. And the Southern Ocean is responsible alone by about 50% of the whole excess of the carbon dioxide taken up by the global ocean. And this is a very huge amount because they cover just 20% of the global ocean. And his figure here, we have by the color, indicates if the ocean absorb or release carbon dioxide to the atmosphere. So the red color indicates that the ocean release carbon dioxide from the ocean to the atmosphere, and the blue color indicates that the ocean taking up carbon dioxide from the atmosphere. And when you can see here very well, all the Southern Ocean is very red color, indicate that they absorb a huge amount of the carbon dioxide. And this is very good for the climate change because the ocean is responsible to mitigate the climate change and the global warming by taking up this excess of the carbon dioxide in the atmosphere. But it has a huge price, a high price for this, that is the ocean acidification. One of the main implications of the ocean taking up carbon dioxide from the atmosphere. And the ocean acidification means that by absorbing carbon dioxide from the atmosphere, the ocean reduces its pH. And the pH is a very sensible variable in the ocean, and it's been quite stable in a very, very long time. And recently, we have been observed a very decrease in the pH in the ocean, and this is very danger because many tiny organisms that live in the ocean is very sensible to the variation in the pH. So it's a huge amount of tiny organisms that is a main food for the greater, larger organisms like fish, for example. So the ocean acidification is a very good, a very problem to the tiny organism, and the tiny organism is a food for the fish, for example. And guess who like to eat fish? So we, human. So yesterday, for example, we ate a lot of fish on the restaurant. So the ocean acidification is a very huge problem for us as well. And this figure here represents most of the processes, but not all of them, that occur in the ocean. So the ocean is there is a huge, many processes occur and at the same time, simultaneously. And this figure looks like a very messy puzzle, and it's real actually. It's like the ocean is. It's a very difficult to understand the processes control the carbon dioxide and the nutrients, for example, in the ocean. And this is why we need to understand better these processes to be able to identify the change that is driven by the carbon dioxide uptake. And this is essentially the importance of our work, actually. And why do we do this? We actually go to the ocean by a vessel. On a vessel, we take samples from seawater in different depths along the water column, and we measure a huge variety of variables, and we measure the organisms that live there and many parameters that enable so that we are able to understand these processes in the ocean. And so this is just an infographic inform a huge variety of variable that we need to understand in the ocean to be able to identify the processes and therefore the chains. And also we are, in a couple of years ago, very into to spread the importance of our work to different levels of society. So we used to go to the children's schools to talk to them about the ocean in the Antarctica and the importance of the ocean in Antarctica. And sometimes we take them and bring them to the laboratory at the university to see what we do in the lab, you know. And we also have put many efforts to spread the knowledge of the ocean in the Antarctica through the social medias, essentially here in Brazil, because we use very much the social medias, and we also made some literature we believe that is more accessible for different level of people to understand it, you know. And that's it. Thank you very much.
Thank you very much, Tiago. Maybe one more question to you. So, as we see, the Southern Ocean really plays a huge role in carbon uptake. And can you explain what happens if its capacity weakens and how it affects cryosphere, how it affects the Antarctic, for example, which is right next to, or the whole global cryosphere?
Sorry, can you repeat, please, because it's quite noisy.
I'm sorry. Of course. I was just asking, so Southern Ocean has this huge role in the carbon uptake.
Yeah.
And if it weakens, if it doesn't have this capacity anymore, how does it affect the cryosphere, the global cryosphere?
Yeah. Actually, the Southern Ocean is so important to taking up carbon dioxide because it's a region that we have a very important region for the water mass formation. Water mass essentially is the water that going down deep in the ocean bring this carbon dioxide from the sea surface into the deep ocean. And this carbon dioxide stay there for very, very long time. And as Joseph said, when we put fresh water in the seawater, we reduce the density of the water and therefore the capacity of the water to going down into the deep ocean. And therefore we will, sorry, it's quite noisy. And therefore we will stop the carbon cycle to go into deep the ocean. And this will be positive feedback for climate change, you know? So essentially, the ocean is important because they're taking up carbon dioxide from the atmosphere. And if you reduce its capacity of taking up this carbon dioxide will be in the atmosphere and therefore will be warm our planet. And this will have positive feedback for the cryosphere, like sea ice and glaciers and everything. Thank you.
Yes, certainly sounds very scary. Thank you for warnings. Let's now go to the next presenter, Ellie Miller, who works on ice sheets, biology, and science communication, connecting fieldwork with public understanding of climate change.
Awesome. Thank you so much. Sweet. So my name is Ellie Miller. I'm a PhD student at Colorado School of Mines in the US, and today I'm going to talk to you a little bit about groundwater in Antarctica. So a little bit about me. I'm a paleoglaciologist and isotope geochemist, so I use isotopes to figure out what past ice sheets were doing, just to give you some context for this presentation. And if you're unfamiliar, groundwater is any water that's found beneath the Earth's surface. And it can get there in a couple of ways, most commonly via precipitation, either as rainfall or snowfall, but glaciers actually play a really big role in modulating groundwater systems around the world. And when we think about groundwater around the world, I think we're typically thinking about drinking water sources, and you can see a very simplified illustration of where these exist on our planet. But you'll notice here in this figure that groundwater systems are often missing from our ice sheets, such as Greenland, and Antarctica isn't even represented in this figure. So what's happening under these big ice sheets? So in the glaciology community, there's sort of been this understanding that the shallow groundwater system was all there is, and it was maybe some interconnected lakes and channels. But in the past couple of years, there's been an increase in understanding that there's actually a pretty deep groundwater system under most of our world's ice sheets that's comprised of both a shallow and deep component, and lots of water can be stored in these permeable sedimentary basins. And that's really important because water at the base of an ice sheet directly influences how it behaves, from how fast it moves velocity-wise to the different sedimentary features that it can form. So it's really important to understand what water is there and how it's moving around. And all of this represents a missing piece of the Antarctic water budget. In some parts of Antarctica, these permeable sedimentary basins can exceed 4.5 kilometers, so we're potentially underestimating the amount of water that's under Antarctica by around 50%. And because of this, a lot of people have started exploring the relationships between ice sheet change and how groundwater is moving, and you can see a very simplified illustration of that on the screen. So in a system where your ice sheet is growing and you're accruing mass, you're actually having water be pushed into the groundwater system because of the increased pressure regime. And then alternatively, in a system where you're losing mass and the ice sheet is thinning, you're having water leave that permeable sedimentary basin. However, these sorts of relationships in their very simplistic form have only been explored on contemporary timescales, so sort of creating a limitation in our understanding of how these hydrologic systems evolve. And here's some data from that contemporary study. You can see that the cooler colors represent parts of the ice sheet that are losing the most mass and are thus expelling more groundwater. And then the air conditioning just turned on. Oh, it's raining. Oh, okay. And then, the warmer colors represent parts of the ice sheet where you're gaining mass and groundwater is actually being pushed into the subsurface. But what about longer geologic timescales, which is what I focus on? So I typically think about the last glacial maximum, which happened about 20,000 years ago. And you can see in these figures, Antarctica was a little bit puffier, and we also had larger ice sheets in the northern hemisphere. Unfortunately, we don't have the modern technologies of today to be able to get at the different ice sheet thickness changes that happened. So we have to get a little creative in the methodologies we use to actually reconstruct these glacial histories. And so that's where cosmogenic nuclides come in. This may sound like a scary term, but I'll try to break it down as quickly as I can. These are certain types or special classes of isotopes that are produced when the Earth's surface is exposed to the atmosphere and can thus start accruing these isotopes in known concentrations. So they're really helpful in glaciated environments because you continually have new surfaces being exposed, starting these isotopic clocks and telling you something about the glacial system that's in that area. This represents it a little bit more graphically, and you can see the rock in orange at your highest elevation will first be exposed to the atmosphere and thus exhibit an older age signature than, say, the darker purple one at the bottom. And this type of work has been done in Antarctica for many, many years. And I've gone ahead and compiled all of the glacial histories that we can based on available data at 61 sites around the continent to sort of inform this study. So once we piece together these ice thickness histories, we can plug them into our hydromechanical model, where the hydromechanical model takes your ice thickness, which is shown in the maroon line, and tells you something about how the groundwater system is behaving along that same time step. So you can see really rapid spikes in your groundwater exfiltration during times when you also have more rapid ice sheet thinning. And if you take this across the 61 sites I mentioned previously, there's not a lot of exciting information here. Groundwater exfiltration over the last deglaciation was overall pretty low. But what you can notice is that there's a couple points, specifically at 5 sites, where groundwater exfiltration over the last deglaciation either matches or exceeds modern levels, telling us something about the hydrologic system and its activity over these longer timescales. And I've also gone ahead and highlighted the specific basins where these relationships are taking place, just to give you an idea of how they're spread out spatially. But why do we care and why does this matter? Hopefully this talk has illustrated that groundwater responses can be very dynamic and sort of challenge this paradigm that these systems are very stable over long time periods. Hopefully it highlights as well that subglacial groundwater and the presence of it beneath an ice sheet can also accelerate mass loss. And finally, a lot of our predictive ice sheet and sea level models fail to capture these relationships between the shallow and deep groundwater system, potentially throwing off estimates of both change and sea level rise over the next few years. And so I always like to end my talks by saying the past is the key to the future. I think there's a lot we can learn from paleoclimate to give context to modern climate change, and I just want to say thank you for your attention and thank you for listening.
Great, Ailey, thank you very much. Maybe just have the micro back
Yes.
for a second.
Sorry, it's really loud.
I hope you can hear me now. Sorry.
Maybe?
Try to move a bit to the side.
Maybe that's good.
Let's try it. Yeah, so you're also very active in the science communication.
Yes.
Can you tell us something about your methods, about the most effective translating this very complex cryosphere science to non-scientific groups, especially policymakers and the youth?
Yeah, I think that's a really important thing, and I think it's something all science communicators struggle with, is how do we make these issues relevant to people that aren't directly impacted by them? Especially in the case of Antarctic groundwater, it's really hard to go up to a policymaker and say, hey, you should care about this really specific question, this really specific process that's happened 20,000 years ago and is maybe still continuing to happen. But I think making those personal connections to people's lives, and I think always drawing it back to those big climate signatures, those big sort of emotional pieces of the climate story, is a really impactful way to build a narrative around your science and make that direct connection. And that's sometimes a muscle that's hard to flex, but with practice and with enough conversations of people who are not experts in your field specifically, I think this is a really valuable thing to learn. how do we tailor our messages for different audiences. So that's what I would suggest.
Thank you very much. Yeah, it's very important and very impactful work. Yes. So let's move to the last presenter today. It's Laura Malares Mancayo. She studies polar and atmospheric microbiology, exploring how microscopic life in glaciers tell us about broader climate processes.
Thank you very much, Victoria, for that presentation. So my name is Laura Molares, and I am a PhD student. I'm on my third year of my PhD, and I'm currently at Queen Mary University and the Natural History Museum of London. And today I'm going to be telling you a little bit about my work in progress towards understanding whether microbes that live on one of the most extreme environments of the cryosphere, the glacier surface, are able to survive off of the use of trace gases from the atmosphere alone. So we've been talking about glaciers a lot, and we know that these are processes and the glaciers are moving over thousands of years. But if we think of a smaller time scale, glaciers are actually extremely diverse ecosystems that change on a daily basis, on a seasonal basis, of course, but on a daily basis as well, with extreme changes in temperature and light exposure, creating tiny micro-niche environments that are filled with different bacteria adapted to these specific conditions, such as watermelon snow, sediment, ice surface, as well as cryoconite holes. In these, you have many, many different types of bacteria, such as algae, multicellular, bigger microorganisms, as well as bacteria, that have all these special adaptations that allow them to survive these extreme conditions. Now, one of the main things that I think is the most difficult thing that they have to survive is a lack of nutrients, a lack of energy sources. And for this, they have flexible metabolic strategies that allow them to use any of the things that they have available in their environment. Now, we still don't understand exactly what types of metabolisms they're doing on glacier surfaces. So there's this growing body of literature that suggests that in extreme environments, microbes might be able to use atmospheric sources of energy, that is specifically trace gases such as carbon monoxide, methane, or hydrogen, and use this as an alternative resource to solar or geological energy, i.e. not photosynthesis or something that might be happening due to geological activity. This is particularly interesting in polar regions because these bacteria might experience up to 6 months of total darkness in the polar night, and we still don't know exactly how they're surviving through the winter in the snowpack with nothing else to consume. As such, one of my main research questions of my PhD is to look whether these communities could be sustained through the use of atmospheric sources of energy. So in order to ask this question, I used two main types of methodology. One is this DNA approach and an activity measurement approach. And for the DNA approach, what we do is we take samples from surface environments and we look at the DNA and we ask two main questions. Who is there and are they known to be able to use these gases? And what types of genes do they have? Do they have the enzymes that are needed to be able to oxidize these gases from the atmosphere? So the first thing that I did before going to the field was I collected data from all around the world, from surface glaciers, and on the x-axis here, what you can see are the names of different glaciers that you can see where they come from in this map, from cryoconite ice and snow, the types of environment that I talked about before, and on the y-axis, you can see the names of different enzymes that are used for different metabolic pathways. In blue are the enzymes that I'm interested in, and for context, we had no idea whether these enzymes were present in these communities. So what we wanted to see was, are they there? Can they potentially be doing this on the glaciers? And the colors represent whether these enzymes are there. So if the color is really dark, that means the enzyme is there in all of the community, and the lighter colors means that only a fraction of that community has it. So what you can see here is what I was talking about, that these communities have very flexible strategies and are able to use sulfur, nitrous compounds, as well as many different sorts of carbon sources. But what's really interesting is that the ones that I'm interested in are also present. So this gave us a clue that perhaps this could be happening. And with that information, we went on the field. So my team and I, we mostly work on Svalbard. It is an archipelago above Norway on the on the Arctic Circle. And we have access to multiple glaciers where we collected multiple samples, but also we were able to go in different seasons to see whether this changed with the season. So as I mentioned, we collect fresh snow as well as bulk snow. We collect ice, as well as ice cores in the winter. And we collect craconite sediment from the glacier surface. What we did with these samples is we incubated them at low temperatures, and we covered them so that to replicate a dark environment, so that the only energy that they had was the gases that I was going to feed them. So I added known concentrations of the gases that I was interested in, and what we wanted to see was whether these concentrations would decrease, because if they decreased, that meant that they were actually absorbing those gases and using them to survive. And so what you see here are, on the x-axis is the time that we incubated them. So this went on for about 2 months. And on the y-axis, you see the concentration. So what you can clearly see is that for hydrogen and carbon monoxide, for all 3 glaciers, you see a decrease. That meant they were consuming these gases. We were so excited because we had no idea whether this was going to happen. And also the fact that it was happening from samples from all 3 glaciers. And also, interestingly, methane wasn't being consumed. So for some reason, only these 2 gases they're using. So what have we shown with this? So we've been able to show through 2 different ways of analyzing data that we have evidence that these surface glacial communities have the potential to oxidize trace gases as energy sources alone. This, again, to put it into context, gives us a clue as to how these microbes could be surviving through the winter by literally just breathing air and surviving through the whole time, albeit at very low amounts of energy, but it allows them to keep going until a better time comes. Also, if you consider that these are only 3 glaciers, but if you scale it to a global scale, what this could mean is that snow-covered environments could all be breathing these gases. And if we don't know that this is happening, we can't put it into our models. We don't know that this is also being part of the biogeochemical cycling of these gases. One last thing I wanted to mention is that some of the glaciers that we work on are glaciers that are retreating. So here you can see a picture from the 30s, the 1930s, and a picture from the 2020. And Mitralövenbryn is one of the glaciers that we collected samples from. As you can see, it has decreased massively, as well as all the other glaciers around them. So if we don't know that this is happening, we also won't know what will happen if this environment disappears. We don't know how the local environment will change, but also how the global gas exchange will also be affected. Thank you very much.
Thank you, Laura. Thank you very much. Maybe just coming back to the last slide again, can you maybe tell us more about how these microbial communities already respond to the glaciers melting?
Thank you. So we don't exactly know how these communities might be changing. It is a topic of investigation at the moment. We know that these communities are highly resilient to these changes. I mean, these are bacteria that are used to extreme changes, but we don't know on the long term how it's going to affect them, how it's going to affect who remains there, what they're doing, and how it's going to change the local atmosphere or even their own environment. So this is why it is so important to keep doing science, to keep funding the science, especially to do monitoring during the winter time. There is a lack of information of how these bacteria are surviving in the winter, and with that, what their activities like, what they're consuming, what they're not. So with the melting, not only through in the summertime, which is what we tend to think when we see these pictures, we also have to consider what happens when the temperature changes, importantly, in the winter. How will this affect later on in the year? So yeah, we need to keep monitoring because we don't really know.
Seems like still a lot of things to be done for us. Thank you very much, everyone. I will just have one question to all of you. Please think about it and formulate your key message based on your research to the negotiators here at COP30. What would that be? Josep, you want to start? Yeah.
Yeah, I think that sometimes we look at the polar regions like something very remote that we don't know what is happening there. But if I have to highlight something of our presentation, is that the changes that we are observing in the Arctic or in the Antarctica have global implications, because these parts of the world are cooling all the planet, and if we don't have glaciers of snow or ice sheets, all of the oceanographic and climate patterns that we were presenting will be completely different.
Well, what I would say is that most of the issues, environmental issues that we are talking about here, in the ocean, in the glaciers, and different environments, is completely unprecedented, you know? And most of them is completely irreversible. So we have no idea, for example, how can you frozen thousands of tons of water that melt from the glaciers and from the mountains and in the ocean, you know? We have no idea, we have no technology to do this. And the impact we know very well that we are talking about here. So the main message is this, you know, we do need to take action now, because we have no idea and nobody in this planet can do something to undo what we are doing now, you know? That's it.
Yeah, those are all great points. And I wanted to echo something Laura said at the end of her talk about we need more money for this type of work and more awareness for this type of work. I think there's a lot of questions that are still unanswered and a lot of processes that we need to learn more about to create more accurate prediction frameworks. And yeah, especially coming from like a US context where science funding is under attack, I think this is more important now than ever, especially in the conversations that are happening here at COP.
Yeah, I totally agree with everything that has been said, and it's tough because that's what I was going to say. But no, I mean, I think at the end of the day, all of this is completely true, and all of these different environments that we've talked about are all completely connected. We talked about biology, we talked about paleoscience, we talked about current oceanography, and everything is linked to each other, and all of these systems are slowly collapsing due to each other. So we need to have a very holistic view of the whole situation and listen to the scientists and, you know, pay attention to how everything is telling us what is going on.
Yeah, thank you very much. Thank you very much, everyone, for your presentations and your talks. And yeah, for your really great work doing this research, very impactful one, and as well as participating here and advocating for the cryosphere.